Hello, this is Thomas Reese, and this is my project for Modern Geometries with Professor Misseldine. And I've decided to open the presentation on a bit of a foreboding passage, supposedly an inscription on Plato's Academy in Athens, though cannot be confirmed that that was actually there. A bit of an apocryphal story, but I like to think it was. So, this is my presentation on my research into ancient Near Eastern geometry, specifically from pre-classical Egypt all the way up to Euclid of Alexandria. So, we'll be covering ancient Egypt, ancient Mesopotamia, pre-Alexandrian Greek influence, Persia, and Alexander, which is some historical context on the transition between these earlier mathematical developments and the later ones, as well as some mathematicians from the city of Alexandria or its sphere of influence, and Euclid himself. So, without further ado, we'll start with Egypt. So, one of our best mathematical sources for Egyptian geometry comes from the Ames papyrus, dated to about 1650 BC, and it was a copy of an earlier text dating from about 2000 BC. And the Ames papyrus is named after the scribe who copied it down. Now, most of Egyptian geometry from this time period was purely practical, because it hadn't really been developed to the point where it was used abstractly or purely theoretically. And the primary uses of geometry in Egypt at this time was to survey the Nile floodplains, which, being floodplains of a river, every year would flood and then recede back, which would change the geography of the shore around the river. And this would mean that people would need to survey the land and reallocate it based on how much was gained or lost to each plot. And they additionally used geometry for architectural design. For instance, a very famous example, the pyramids. Takes a lot of planning to get something like that off of the ground. So, yeah, that was probably the biggest example of how they used geometry. And one example, unfortunately, one of my file conversions seems to have put the shadow on top of this example bar here, but an example of Egyptian geometry is in the Ames papyrus. It states that an area with the area of a circle with diameter 9 is the same as the area of a square with a side length of 8. So we can get that the ancient Egyptian value of pi that they were using was 256/81, or about 3.16, which, all things considered, I've seen worse approximations of pi used. So that's not bad at all, considering the time period here. So now, moving on to Mesopotamia. Now, this covers a bit of a broader period of time, from the ancient Sumerians up until the Babylonians, but similarly, it began mostly having to do with the practical applications, the surveying and architecture. However, the Mesopotamians did develop abstract geometries and algebra. For instance, they formulated and solved quadratic and Cuban's equations as a form of geometry. Oh, a bit of a typo there. And they additionally had knowledge of the Pythagorean theorem, and actually we have tablets that have been found to have Pythagorean triples written out. And then we also have the mathematics of pre-Alexandrian Greece, such as Thales, Pythagoras. And then this increased even further the emphasis on abstract mathematics, less and less practical application, and more of the theoretical. And in this vein, some, like Plato and Pythagoras, even held that mathematics had some spiritual significance, that there was some link between mathematical and divine. And then there were also some, important mathematical truths that were discovered at this time, including the existence of rational numbers such as the square root of 2. So now for some historical context. So from about 500 to 300 BC, the Achaemenid Persian Empire ruled over most of the eastern Mediterranean, which, being under a single government for a long period of time, allowed for a lot of cultural exchange. So a lot of these Egyptian mathematics, Babylonian mathematics, and Greek mathematics were able to interchange and develop over time. And eventually, circa 320 BC, the Persian Empire was conquered by Alexander the Great. And his successor kingdoms of Alexander the Great introduced Greek as a universal language in the region. And this additionally helped the cultural exchange and allowed for not only a very well documented period of history, but a period of history that that had a lot of cultural and, especially for what we care about, geometrical and mathematical progress being made. So, and one of the best examples of this progress was in the city of Alexandria, which was and is in northern Egypt. And this city was the central location for both cultural and mathematical progress in this time period and in this location. And most of the major mathematicians of the era hailed either from Alexandria or from its immediate sphere of influence. So, for a couple of examples of Alexandrian mathematicians, we have two of my personal favorites, Eratosthenes and Aristarchus. So, Eratosthenes was able to use the shadows of poles and the known distance between two cities. He calculated the circumference of the Earth for his methods, is incredibly accurate scale, about only 10% off, if I remember correctly. And using the size of the Earth, Aristarchus, a different mathematician, also in Egypt, was able to use the size of the Earth's shadow on the moon during a lunar eclipse, in order to calculate the size and orbital radius of the moon. And he did this also with surprising accuracy. He got pretty close to the size of the moon, I believe about 20% off, but the orbit of the moon he assumed to be a perfect circle, and the radius of that circle is actually in between the greater and lesser axes of the ellipse that the moon's orbit actually is. So that's actually quite interesting. He was able to get it that close. And then also, he tried to calculate the size of the sun through a significantly more complicated method using the phases of the moon. But it was significantly less accurate. However, he did figure out that the sun had to be bigger than the Earth. And he was actually one of the first people to propose a heliocentric model, though it did not catch on. In this vein, as I was researching for this project, actually, the famous mathematical YouTuber 3 Blue 1 Brown actually posted a video about Aristarchus's astronomical calculations, and I would highly recommend checking it out. It's a very interesting and a much deeper dive into the mathematics he used. Then we come to, you know him, you love him, it's Euclid. Euclid was one of the first people to try to completely axiomatize geometry and mathematics as a whole. And he made a few mistakes. He has a couple logical errors and a lot of implicit assumptions that he does not express, but it still was the bedrock of geometry for centuries afterwards. And frankly, it still, even to this day, serves as a bedrock of our geometry, as the most popular geometry used in math and science to this day is called Euclidean geometry. So, here we have listed Euclid's 5 listed axioms, apart from the implicit assumptions he made. We have 1, that a line segment can be drawn from any point to any point. A line segment can be extended infinitely into a line. A circle can be constructed with any point as a center and any radius. All right angles are equal to each other. And if a line intersects 2 other lines, and the internal angles on the same side of that line are less than 2 right angles, then the other 2 lines intersect on that side. So, this 5th one is probably the most famous, the Euclidean parallel postulate. And this one was one of the, you can kind of think of it as the Achilles heel of the geometry, because it implicitly assumes that you have no curvature in your geometry, that lines remain equidistant from each other at all times, which is not necessarily something that will always hold true, and that there are many useful models that don't apply this. And here are a list of some of my sources. The majority of the information came from A History of Mathematics by Ute Mersbach and Karl Boyer. actually quite a fascinating book. It has a lot of information outside of geometry that I found incredibly interesting, including different kinds of counting systems and the development of algebra. A lot of the information regarding Euclid came from Geometry by Its History by Alexander Osterman and Gerard Wanner. And I also have a copy of Euclid's Elements with the Greek text and a translation. The Greek text was compiled by J.L. Hingberg and translated by Richard Fitzgerald. And that's it. Thank you very much for anyone who's watched this, and I hope you enjoyed. Thank you very much.